Hello students, so this is acid-base titration part 2 and these are the focal points of acid-base titration part 1 which we have already covered in our previous videos and lectures. We have already covered primary, secondary standards and definition of primary standard, definition of secondary standard, methods of titration, then acid-base theories, the Arrhenius theory, Bronsted-Lowry theory, definition of Lewis theory, examples of it, then acid-base indicators, definition of acid-base indicators, and a little bit about the choice of indicators. And we have also plotted a neutralization curve in between strong acid and a strong base, where strong acid was hydrochloric acid and strong base was sodium hydroxide. Now in this titration part 2, in this video we'll be concentrating more on titrations of weak acid and strong base, titrations of strong acid and weak base, and if time allows we'll also cover weak acid weak base titrations and titrations with polyprotic acids. So this is the curve, neutralization curve, pH curve, which we have already covered, which suggested us the use of phenolphthalein, litmus and methyl orange over the entire pH range at which endpoint was attained in a strong acid strong base titration. It suggested that any of the indicators listed with the suitable will be suitable, and they all can change, they all change in vertical portion, and methyl orange can also respond to the change in color at acidic pH. Litmus responds to change in pH at neutral pH, and phenolphthalein shows change in color at basic pH, pink color. So all these three indicator systems, these are the choice. This can be the choice of indicator. This can be chosen as indicators in between the titration of strong acid and strong base. To continue with, we have now titration in between weak acid, which is 0.1 molar acetic acid or ethanoic acid we say, and strong base, that is 0.1 molar sodium hydroxide. Now as we see the shape of the curve in case of strong acid and strong base titration, it is perfect sigmoidal curve depicting a sharp change in pH. Here we can see the pH starts in the case of hydrochloric acid, the pH starts from around 1, and but because acetic acid is a weak acid and 0.1 molar solution of acetic acid, weak monoprotic acid is taken, and because it is not completely ionized, so the pH of the reaction at the very onset is 4. Okay, and when we add slowly to it sodium hydroxide, 0.1 molar sodium hydroxide, which is acting as a strong base, there is a steady pH change on account of formation of conjugate base, which is formed from weak acid, that is acetic acid. Okay, CH3COO minus, the conjugate base, is resulting in a steady pH change which raises to around pH 6 units, and then when entire amount of acetic acid is neutralized, then there is a change, sharp change again in pH, and less than half a drop of sodium hydroxide also shows a prominent change in pH from 6 to 11.5 with this curve, and then any excess addition of 0.1 molar sodium hydroxide, a strong alkali, results in stable pH range. Same can be seen with the help of an example. This is also the curve plotted between 0.1 molar acetic acid and 0.1 molar sodium hydroxide, which says that there is only this much sharpness at end point at basic pH. This indicator system which is resulting change, a physical change or a color change at basic pH can be used, whereas it was not the case in case of strong acid and strong base. Acidic pH, neutral pH and basic pH, three of the indicator systems, all the three indicator systems which are responding at the entire pH range in case of strong acid and strong base titrations can be chosen for titration. But here you can see the strong change or a sharp change is in between 8.5 to 10.5. So the indicator systems like phenolphthalein and thymophthalate, who are in between the basic pH ranges and show the change in color at basic pH, can be used for titration of weak acid and a strong base.